Nowadays we're constantly hearing micro this and nano that, but what does it all mean?
We'll first start by comparing the size scales of objects we are more familiar with, using the program nanoscaling, which is created by Nanomission. In the upper left-hand corner is an indication of the object we're currently looking at. In the upper right-hand corner is a scale bar relating actual size with the size shown on the screen. Finally, the bar on the bottom of the screen indicates the approximate size scale regime that we're currently looking at. First, we'll travel from the size scale of a human being all the way to the Sun. The average height of a human being is about 1.6 meters, whereas the diameter of the Sun is about 1.4 times 10 to the 9th meters, or 1,400,000 kilometers. That means the size of the Sun is approximately 1 billion times larger than we are. We've seen that the Sun is 1 billion times larger than a human being. Now a nanometer is 1 billion times smaller than a human being. Hence, to a nanometer, we are as big as the Sun. In short, there is a vast unexplored space between us and the nanometer. A micrometer, or a micron, is 1/millionth of a meter, or 1,000 times bigger than a nanometer.
To give you a better idea of scale, the width of a human hair is typically around 100 micrometers, or 100,000 nanometers in diameter. How many atoms are in a strand of hair? Well, let's figure it out. First, we calculate the volume of hair in cubic nanometers. We get a huge number, 400,000 trillion or 400 quadrillion nanometers cubed. On average, there are 125 atoms in every cubic nanometer. So we multiply by this value to find the enormous number of atoms present in a single strand of hair. Therefore, the nanoscale is very real and very small. Structures with features less than 100 microns in size cannot be seen easily with the naked eye. To give you a better idea of scale, a sheet of paper is about 100 microns thick. We will now observe increasingly small objects and biomolecules as we travel from the size scale of a human down to the nanometer. An ant is about 5 millimeters in length. Cells are generally tens of microns in size. Bacteria are just a few microns. And pathogens, such as viruses, are hundreds of nanometers. Finally, we get down to just a few nanometers with nanotubes and fullerenes, such as the buckyball shown here.
Whether we are traveling down a busy street or relaxing outside a coffee shop, our lives are positively impacted by the work of engineers. While engineers are out there paving the way towards safer cars and alternative fuels, an increasingly active area of research is the development of ever smaller components that make up everything from your laptops and cell phones to powerful new medical devices. More often than not, macroscopic structures are built by picking and placing objects piece by piece. But to do this at extremely small scales, where objects are too small to see with the naked eye, we need to use different methods. One such method involves the phenomenon known as self-assembly. In nature, many things self-assemble. Flowers start as tiny seeds and follow a natural progression until they reach their beautiful mature forms. Rocks and crystals also form by self-assembly, with tiny molecules rearranging into complex three-dimensional geometries all on their own. Motivated by this phenomena, Dr. David Gracias and his students at Johns Hopkins University in Baltimore, Maryland, developed a novel way of transforming two-dimensional shapes into very precise three-dimensional objects. Consider, for example, the construction of a paper cube. Dave, a senior in Dr. Gracias' lab, attempts such a feat. He begins with 6 cutout squares. By carefully taping the squares together to form sides, Dave is eventually able to make a cube, although it takes him a few minutes and it has many imperfections. Tim, on the other hand, is a graduate student, and he takes a very different approach. He simply cuts out a single shape, which he then easily is able to fold into a cube, saving a lot of time. In the laboratory, we use a process from the computer chip making industry called photolithography to make our 2D shapes on a miniature scale. First, a mask is created. It is used to expose a specially prepared silicon wafer, and the areas that are hit by the light dissolve away. This leaves a mold behind which is filled with metal, forming the cube faces. This process is repeated, connecting the faces with another metal that functions as the hinges. Once the two-dimensional structures have been prepared, they are heated until the hinges begin to melt. As the hinges melt, they ball up in order to minimize their surface area, and since they are attached to the square faces, this brings the faces together and eventually forms a cube.
What force makes this self-assembly possible? A phenomenon known as surface tension. A natural property of liquid is that it needs to minimize its number of boundary molecules. To achieve this, the liquid minimizes its outer surface area by contracting into the smoothest shape possible, the sphere. Surface tension forces on the micro and nanoscales are very strong, making it an extremely attractive option to drive micro and nano self-assembly. Real-world examples of surface tension include a dew droplet sitting on a leaf, puddles of water balling up on a smooth surface, and objects sitting on a water surface. Now we'll see how this force is used in self-assembly. The temperature is raised to the melting point of the solder. The liquid solder then balls up to minimize its exposed outer surface area. And finally, the surface tension force rotates the faces upward. Shown here is an actual video of the surface tension driven self-folding process. The self-folding process makes mass production of these polyhedral containers possible. These containers can range in size from several millimeters all the way down to hundreds of nanometers.
A cleanroom is a controlled environment where extremely small micro and nanoscale structures and devices are manufactured. Cleanrooms are required because air is full of dust particles, which are sized typically in the submicron to millimeter length scales, and are therefore much bigger than the devices being fabricated. A cleanroom is a room in which the concentration of airborne particles is controlled to specified limits. Typical office building air contains enormous quantities of particles that are about a half micron in size. This number is anywhere from 500,000 to 1 million particles per cubic foot of air, whereas a Class 100 cleanroom is designed to never allow more than 100 particles per cubic foot of air. The only way to control particulate contamination is to control the total environment by a combination of filtration and proper use of materials. Cleanrooms are designed to achieve and maintain airflow with a uniform velocity along parallel flow lines, extending from the ceiling to the floor. This type of airflow is called laminar flow. The more restriction of airflow, the more turbulence, and this turbulence leads to lateral particle movement, which may cause particles to accumulate onto surfaces. White light contains ultraviolet rays that are harmful to light-sensitive material